All right, now that we've gotten the rate of accumulation, what we need to do is think about the flux, the net flux of linear momentum. And again, just like we did for conservation of mass, we're only going to think about one side and we'll sort of extrapolate our results. All right, so we're going to take our volume here, and instead of drawing it this way, we're going to say, okay, here's my y, here's my x, here's my volume from the side, and I have this face here, and this face has an area of dz dy, right? And what we're going to do is think about the flux of linear momentum in the x direction like this, all right? And then we'll think about it in another direction. So on this side, what do we have? All right, what is the flux in? Well, it is m dot. All right, and again, we're only thinking about net of flux of the linear momentum. And remember, we're going to keep these equations in the x direction. So the linear momentum in the x direction is m dot u. All right, and that m dot, again, we can expand out. So it is really rho times the volume flow rate, and the volume flow rate is u. And again, dz dy times u, right? So if we just rearrange this a little bit, all right, it is rho uu dz dy. All right. Now the flux out, all right, over here, the flux out, all right, is really rho. And the only thing that can change is u. So we really want to evaluate u at x plus dx and u at x plus dx. And then dz and dy can't change, right? Now, u at x plus dx is going to be a Taylor expansion again. So remember, we talked about that earlier, all right? And in fact, we're going to keep those two together like that. So that means that it is u plus du dx times that different dx, all right? And rho u at x plus dx is going to equal rho u plus, and we're going to keep rho in the derivative like that, times dx, all right? So if we take these terms and plug them into this, we get that rho, hold on, let me write it. Yeah, I'll write it this way. Rho u plus d rho u dx dx times u plus du dx dx times dy dz. All right, now let's combine some terms and multiply some things out. So we'll get rho uu plus rho u du dx plus u d rho u dx. Now, if you look at this term and think about the chain rule, this is actually d rho uu dx. So let's just erase all of that and write that because it saves some space on the slide. All right. And times dx plus the u dx d rho u dx dx squared dy dz. Now this term here, I'm going to circle it in red, okay, we're going to ignore. Why are we ignoring this? We're going to keep these equations linear. You see this? I'll circle it in blue, right? We got a dx squared and we got two derivatives times each other. That's a quadratic term. It's a non-linear term. All right? So we're going to ignore it. We're going to ignore it, which means that this thing now is just rho uu plus d rho uu dx dy dz. Okay? So if we do that, all right, on another face, so let's see, here's a face, here's our y, and here's our x, and now we think about this side, which will be dz dx. What's going to be different? We still are going to have m dot coming through, right? And this time, and we're still going to have it times u, right? But this time m dot is rho v. Why? Because the velocity is in the y direction. U, all right, well, rho v, and then you would have your dz dx, all right? Excuse me. All right. Times u, which means you get rho v u dz dy. All right, so the difference is if you look at the velocity through this other face, your m dot is going to change what velocity it is, but you're still thinking about the x velocity. All right, so if we do this through all the faces, all right, you would have in and out. Here's your fluxes. In the x face, that x direction, you would have rho u dy dz, and here you would have rho u dy dz plus d rho u dx dx dy dz. And in the y direction, you'd have rho vu dx dz, and in the out direction, you'd have rho vu dx dz plus d rho vu dy, all right, dx dy dz. All right, the reason there's a dy there is because we would be going in the y direction. That's where the Taylor expansion would occur. In the z direction, you get rho w u dz dx dy. Why w? Because the flow rate is in the z direction, so the w, the z direction, is setting the velocity. Then you'd have rho wu dx dy plus d rho wu, and this times dz dx dy dz. All right, so if you look at the net flux, which remember is out minus in, all right, then this term becomes, if you take all these together, all right, in any one particular direction, right, you're going to get all of these d rho uu dx plus d rho vu dy plus d rho wu dz, all of those times dx dy dz. So that is the net flux, all right, which means that if we think about our rate of accumulation plus net flux, which was the first part of the conservation of linear momentum, what do we get? We have d rho u dt plus d rho uu dx plus d rho vu dy plus d rho wu dz, all of that times dx dy dz. All right, so that's part two. The next part is we got to figure out what the forces are, and that's a lot worse.